you doing? Okay, what page are we looking for here? 30, okay. Page 30. Wow, must have been pretty hard. Only 1, 2, 3, 4, 5, 6, 7 people got this one right. Solution to last month's pump problem. Let's see, what did we say it was? Do you remember?
Low voltage fuse, balloon on low voltage. Control voltage
Short to
fuse.
ground.
Really?
Short to ground fuse problem.
Let's see. The next step we need to take on the repair of this unit.
On the 24 volt
is blown
circuit.
fuse on the control side of the diagram.
Yeah.
Okay, blown fuse on the control side of the control side means the secondary of the transformer. And I said usually it's a short, right? It's a short on the secondary somewhere, okay? When we tested at points 3 and 4 on our diagram, we read 24 volts, but moving the points to 3 and 5 showed a 0 voltage reading indicating a blown fuse. Check all the connections and check the control wiring for possible shorts.
Yeah.
Huh?
Yeah.
And replace the blown fuse. Okay, if you would have sent in or done this on the computer and sent it to them on the computer, your name would have been in to win this prize. They won a electronic clamp-on head for a field piece. And a video. Yeah.
I sent
and
it.
they would have put your name in there.
I sent it. Okay, I sent it in. They told me I was right. Did what you said, and they said that they have a cutoff date. And I said, well, I faxed and mailed it to you. And they said, well, we didn't look at them. If you went online, it'd be better. Just let you know.
Oh, you faxed it.
And I
didn't go online.
Yeah, I faxed it and mailed it to them. And I talked to the editor. His name is Peter.
Oh.
And he said that I was right, but they have a cutoff date and they have deadlines to make.
Those stupid bastards. Okay.
Just to let you know. You were right. You're right.
But I was right on the
Exactly.
diagnosis.
100%.
Okay.
100%.
Okay, let's take a look at this. Let's take a look at this one right here. I'll read it real quick to you. Why is this making so much weird noise? Maybe I should stand where I'm really better. That's right there. Stuff in the way, maybe. I don't know. Okay. I may have to start wearing glasses.
You can borrow mine. I don't want mine.
Okay, the comfort cooling season is in full gear, which means the HVAC technician can be called upon to service just about any type of equipment, even smaller units that are gaining popularity with home offices and moderately priced models. Our troubleshooting situation this month relates to a customer who is called to say that their wall-through PTAC, which is a package terminal air conditioning unit, it's a wall unit.
Okay.
Like that one there. When you arrive at the customer's home, you find that the refrigeration system is actually a heat pump, and that the unit is running in the cooling mode. This particular design of unit uses a standard reversing valve, as you would find in larger HVAC systems, and a metering device system that forces the refrigerant through a capillary tube in either direction, depending on the cycle selected. You quickly eliminate the possibility of the airflow or electrical system problems and begin to focus on the refrigeration system itself. With an access valve installed on the true suction line, the true suction line would be the suction line. I guess you're going to have to share that between the three of them. The true suction line. Now, the true suction line is the middle one. Take a look at the little diagram down below. Now, you see the middle one, the middle low pressure where it goes to the accumulator.
Okay.
That's where you would put your low pressure. That's where you put your line tap. Now, those don't come with line taps.
Mm-hmm.
You got to put your own line tap in there. There's no place to put a gauge on. You got to put your own line tap so you can put your gauge on. Those don't come with it like a regular air conditioner. They're all sealed at the factory.
You have to empty the system or?
Well, no. Let's say you wanted to see if there was any freon in it, or if it was reversing, or what the pressure was. Okay, you'd have to go ahead and take a line tap. Yeah, a line tap.
Like a piercing valve?
A piercing valve,
Yes, sir.
and you'd have to pierce right into it so that you'd be able to put your gauge on. And it stays on there. It stays on. Okay, and the true one would be, see what it says, low pressure, that right there is where you'd put it, where it goes into the, anywhere between where it goes into the middle of the reversing valve, anywhere along there, you can go ahead and tap into it.
When you look at the low side, you don't have to bother with the high side?
You know what? Most people don't even put a valve on the high side on these. They do everything through the low side. You know, it's just that's the way it is, because number one, there's more of a chance of a leak with high pressure, because 300 psi. You know, and you know, you can kind of guess where everything's supposed to be. You know, you'd want like a 40-degree evaporator. And you just look up on the PT chart what that was with R22, and you know, you fill it up to that. Okay, let's see what they say about this. Excuse me. Let me see. Pressure diagnosis of the problem. You also note that there is a slight gurgling sound at the entrance to the indoor coil, which has a partial frost pattern. When you disconnect the power supply, you also notice the refrigerant system pressure equalize, but very slowly. Your troubleshooting question, what is causing this unit to perform at less than its rated capacity? God, that didn't give you much to go on, did they?
Could it be a restriction?
Did they tell you anything about
What the pressures were?
what the pressures were? God, it could be anything.
Sounds like
Okay.
a restriction.
Okay. Well, they put a pressure gauge on. They put a line tap, but they didn't tell you what the pressure was.
Didn't give us any numbers.
Oh, did I miss something? Did I miss that? And you note the pressures as we're showing them in our illustration. Okay. Okay. Suction pressure lower, I missed that, yeah, okay. Suction pressure lower than it should be, and head pressure lower than it should be. Okay, now, what are the two things that will cause head pressure to be lower and suction pressure to be lower?
Restriction in the cap tube.
Okay, restriction?
Cap tube.
Restriction will do it,
Yeah.
because there's not enough freon going into the
Exactly.
evaporator. They said they heard gurgling.
Yeah.
Okay.
What's that?
Now another thing would be low on freon, right? Low on freon would do the same thing. Okay, but let's go back to the gurgling thing. Okay. If a refrigeration system is low on freon and you put your ear next to the metering device, if it's low on freon, what are you going to hear? You won't hear gurgling. What will you hear? Hissing.
Hissing.
Exactly.
Starving.
Hissing.
Starving.
You knew that.
Starving.
How come you didn't say hissing?
Give them a chance.
Okay. Okay, so what's happening here is if it was low on freon, you would hear hissing instead of refrigerant going into the evaporator as a liquid, refrigerant's going into the evaporator as a vapor because you just don't have enough refrigerant. So you'll hear hissing going into the evaporator. The gurgling thing is in fact a restriction. Now, why are you seeing a little bit of frost where it goes into the evaporator?
Or frost, flash gas.
It's metering in, but it's not metering in fast enough for the pressure on the low side to be up where it belongs. It's starving the evaporator. When you starve the evaporator, what happens to the low side pressure? Up or down?
Down.
Down. When the low side pressure goes down, what does the temperature of the refrigerant do?
Goes down.
Goes down. That's why you have frosting. But there's not a lot of frosting. There's just a little bit of frosting. Right? Okay, so that would tell you that it was a restriction. That's where I would hang my hat. So if you want to send in your deal, you can go ahead and send in your deal. Okay. I have something for you guys to do. Where's all my pencils? When you do the circuit board, I don't have a circuit boards for everybody, but you will be able to do it. On the circuit board, you hook up the circuit board just like I showed you up on the board. Remember? Everybody drew it, right? Okay, hook it up just like I did up on the board, and you'll be able to turn the fan on delayed. It's another way of delaying the fan. That's all it is. Let me see, what else? Those 2 units back there, one of them is really pretty easy. It's only cooling. The difficult thing about the only cooling one back there is there's a 2-in-1 capacitor and the fan capacitor. So you've got a 2-in-1 type of a capacitor, which seems to throw a lot of people off. That's why I make you do it. So, so that you can do it here. If you can do it here, then you can do it out in the field. And the other one is a heater and an air conditioner. A little harder. Two-speed fan. Okay? Makes it a little tougher. Don't you guys want to? Yeah, okay. Have you been dreaming about it?
Everything there.
Good. And then, once you do those 2 and those 3 whiteboards and this, okay, I've got a nice big one outside for you to work on. It's a carrier unit with a spark ignition system. Hello.
Many technicians believe that over 60% of their work requires troubleshooting. So today, we'll take a close look at the unit wiring diagram and electrical troubleshooting. But before we proceed, let's review some safety precautions that must be followed. Only qualified technicians should perform service on electrical equipment. Whenever possible, shut off all power when working on electrical equipment. Lock and tag disconnects and circuit breakers to prevent accidental turn on of power. Remove watches or rings to minimize electrical shock hazards. Always wear safety glasses and gloves when handling refrigerants or when brazing. The information in this program is general in nature. Before performing service on any equipment, always follow the specifics of the manufacturer's installation instructions and service literature. If you have any questions regarding the procedure, call your supervisor. Don't take chances. All electrical circuits depend on the flow of electrons to perform the work necessary for air conditioning. In order to have electron flow and to be able to control it, we need 4 items. A source of power, such as a battery, generator, transformer, or a source of commercial power. A path for the electron flow from the source back to the source. This is called continuity. An electrical load to dissipate the energy of the electrons. A circuit without a load is called a direct short. A means of control, such as a switch or a set of contacts. The means of control in a circuit usually is a magnetically operated relay or contactor. When the coil is energized, it generates a magnetic field which pulls the armature toward the coil. The contacts will either open or close the circuit, depending on...
Okay, they're kind of like showing you a contactor here. The armature at the top, when it gets electricity, it makes a magnet and boop, it closes, right? Now some of them close one set of contacts, open another set of contacts. Like on here, see where it says normally closed? Those open. See where it says normally open? Those close. Okay, so that's the way a fan relay works.
Or normally closed contacts. Both types are shown here. This condition is maintained until the energizing voltage is removed. Then the contacts return to their normal position. In many electrical circuits, a coil like this one is the load in the circuit. The symbol for contacts will usually be shown in the position they are in when they have no power on the coil. The closed contact has a diagonal bar indicating a closed circuit. The open contact is shown without a bar. Contacts are a form of switch and only conduct electrical flow. They're not a load, but they can carry voltage to a load when closed. Let's talk for a minute about the connections made in the field for proper electrical operation. The power wiring must be brought from a disconnect inside of the unit to the unit. For electric heaters, a separate disconnect may be necessary to satisfy some codes. Local codes and the National Electrical Code must be observed in any installation of equipment. Field wiring consists of power wiring from the main electrical service to the disconnect switch, and from the disconnect switch to the unit. The power must be shut off at the circuit breakers or fuses and at the disconnect switch to the unit when work is being performed. Control wiring will be run from a remote thermostat to the control voltage connections in the unit. It would be impossible to construct, install, or service a heating or cooling system without the aid of a wiring diagram. In this program, we'll learn about the functions of the components and the interaction between the power circuit, the control circuit, and the thermostat. We'll look at a simple wiring diagram to learn more about them, and then we'll move on to an actual unit wiring diagram. At first glance, the wiring diagram may look complicated, but once you learn the basic steps, it becomes easy to understand. You'll see several styles of wiring diagrams in your work. Some are arranged differently than those we'll show here. They're all designed to show the wiring arrangement of the equipment. You may want to sketch your own version of the wiring if the diagram is complicated or not clear to you. In this part of the program, we'll cover a typical electrical arrangement of a 240-volt single-phase package unit with electric heat. The wiring diagram is composed of 3 major sections. The first section, the component arrangement, shows the physical location of the components as they're grouped in the unit. This is a physical location aid and corresponds to approximate locations of unit components. For instance, the transformer shown here on the unit is in the same location relative to other components as it appears on the physical location section of the wiring diagram. Component arrangement may vary between different models within a unit family. The second section, the wiring schematic, shows the way the components and wiring are connected to produce an operating electrical system. Unlike the physical location section, it does not identify location, but shows how the components are interconnected electrically. Wiring is color-coded by many manufacturers to make it easier to identify particular wires in the unit. The third section, the legend and notes, further explains the components and provides additional special information. Note that the abbreviations as shown on the diagram are explained here. It's always important to read the notes first when looking at a wiring diagram, since they help to explain any unit particulars, such as time delays that are not easily shown in schematic format. This diagram shows a unit usually referred to as an electric year-round air conditioner. It has electric cooling and electric heating components. Later, we'll look at a gas-electric year-round air conditioner with a gas heating arrangement and electric cooling components. The wiring shown here is not for an actual unit, but it is typical, although simplified. In the interest of clarity, some protective devices and wiring have been eliminated so that the basic elements can be easily seen. Let's look at the wiring schematic and simplify it by breaking it down into 3 parts. The power circuit operates at line voltage. In our case, it's 240 volts single-phase power. In other cases, it could be some other voltage and either single or 3-phase. The control circuit, which in our case operates at 24 volts. Other control circuits operate at 115 volts or even 240 volts.
Now, you guys seem to be getting a lot better at reading these schematics and following the electricity. I think doing it and then actually wiring it really helps. You know, like you can see on here, Y is going through a high pressure control and a low pressure control, and then going to your coil, your contactor coil. You guys all know Y turns on your contactor coil, right? So if your contactor coil isn't getting electricity, then you would go, well, power, path, and load. Do I have power? Yeah, I have power. Do I have power at the other end? No. It's the path, right? And if there's a couple of low pressure and a high pressure control, it might be one of those. See, that's how you troubleshoot. If you guys can read the schematic, and that's why I'm so pounding on schematics. If you can read the schematic, you can, any machine, you don't ever have to have seen the machine before. You can read the schematic, then you can find out, oh, these are in the way. I'm going to check each one of those things. So, you know, the other day I ran into a unit I'd never seen before in my life. It was really weird. And it was old, really old. Had a schematic. I read the schematic for like a half of an hour. And I drew just the part I cared about on another piece of paper. Okay? And then I went ahead, I started troubleshooting, I found the problem. So it was kind of fun, you know, because I don't get to do that much work anymore. So it was kind of fun, and it was different. I like different stuff.
The thermostat, in our example, operates on 24 volts, but it could also operate on higher voltage. Some large units have 2 control circuits with varying voltages. Many have transformers with various voltages for electronic circuit feeds. Other units may use the same voltage for power and for control and for the thermostat voltage. Never assume that a control component or wire is low voltage. Any wire or component can have high voltage on it and can be capable of causing fatal injury. The power circuit carries all the large electrical loads such as compressors, fan motors, and heaters, as well as supplying the primary side of the transformer. As long as power is connected, there will be voltage available at the primary side of the transformer. The crankcase heater, compressor, outdoor fan motor, indoor fan motor, or heater are not operating because open switches or controls interrupt the electron flow to the components. If we close the contacts, there will be power flow and the loads will operate. The crankcase heater switch is controlled by temperature, but the contacts are controlled by the relays and contactors in the control circuit. The control circuit relays and contactors, in turn, are regulated by the thermostat. The thermostat has an on-off switch and a thermostat cooling switch, as well as a thermostat heating switch. The thermostat also has a fan switch, which can be turned to continuous operation or to automatic position, whereby the fan cycles on automatically whenever either heating or cooling is called for. Before we run the system in the cooling mode, let's talk about the protective devices in the control circuits. The high pressure switch protects against excessive refrigerant system pressure, which could place a strain on the compressor and system. High pressures will open the switch and break the path to the compressor contactor coil. The low pressure switch protects against excessively low refrigerant pressure in the system, which could damage the compressor. If the system pressures are normal, both pressure switches will be closed and provide a continuous electrical path to the electrical load in the circuit. In this case, the load is C, the contactor coil. The contactor is an electrical coil which, when energized, closes the contacts ahead of the compressor and activates the compressor and the outdoor fan motor. Let's discuss the start of a cooling on cycle. We're going to set the fan switch at auto and have the thermostat switch set to on. Now, when the room temperature rises to the thermostat setting, the TC switch will close and there'll be flow to Y and the safety controls. If the system pressures are normal and both switches are closed, the contactor will energize. At the same time, a parallel circuit will energize the indoor fan relay through the fan switch G and the normally closed contacts of the heating contactor. The energized contactor coil closes the contacts in the power circuit and starts the compressor and the outdoor fan motor, which is in parallel with the compressor. The indoor fan relay contacts also close, and this starts the indoor fan motor. It runs at high speed because we need higher air flow in cooling operation.
Okay, now this indoor fan relay, one opens, one closes, right? And the one that's closed all the time, well, that goes through, either that wheel or the time delay and makes your low speed on, right? Then when you hit G on your thermostat, it closes high speed, and your high speed comes on. This seems to be the hardest thing for a lot of guys because they're looking at it and they're going, okay, how the heck does this work? And I make you guys do two different kinds of relays, fan relays. One is that brown one, and one is that black one. I want you to do both of them because you see both of them out in the field. Okay? So I want you guys to be able to walk up to a unit, see one of those fan relays and go, no problem, I know how that works. You might want to, on a separate piece of paper in your notebook, you might want to draw a nice big schematic of the fan relay. Because the fan relay's in the closet, right? Go in the closet. It's dark in the closet.
Mm-hmm.
You're up in the attic.
Mm-hmm.
It's dark in the attic.
Mm-hmm.
If you can have your fan relay schematic right in front of you there, you go, oh, okay, that goes there and that goes there and that goes there. No problem. So that's why I always tell you, draw a nice big schematic. Because that little schematic they give you, it's not too good. And the brown one, you look at it and it's kind of like embossed, but it's hard to see. So you should all make a big relay out, or a big schematic out of that. So you know.
Sometimes I find the schematic's missing. It's like someone ripped it off.
A lot of times the whole schematic's missing.
Yeah.
This unit that I have back here, that fan has been replaced. The schematic that goes with that unit back there is not correct. And you'll run into this all the time. You go up to a unit, you look at the schematic, it's got the way the fan's wired. It's a new fan. It's wired different. You got to look at the fan, and there's going to be a little schematic on the fan, and you got to make that schematic work on your old schematic. That's why I did that. they don't match. You know, I didn't do it on purpose. Somebody burned out the fan. I put that one in. You know, but it's a good practice because you're going to run into this a lot, where a component's been put in, it's wired different, and it's got its own little schematic on it, like that one has a schematic on it.
Indoor and outdoor fans move air to lower the occupied space temperature. When the desired temperature is reached, the cooling thermostat opens and de-energizes the contactor and the indoor fan relay. This opens contacts in the power circuit, and the compressor, outdoor fan motor, and indoor fan motors stop. The transformer remains energized, and if the temperature of the crankcase heater switch drops below its setting, let's say 65 degrees, it closes and activates the heater to warm the compressor and prevent refrigerant floodback. If constant air circulation is desired, the fan switch can be set at continuous. This will energize the indoor fan relay, and the indoor fan will run to maintain air circulation through the occupied space.
Okay, now when I check you off on your competency for wiring up your fan, okay, a couple of you guys, you had it on fan continuous, not auto, you know, and the fan was running like it was supposed to, but it wasn't wired correctly. I switched it to auto, everything went off. It's supposed to be on. Right? Little problem, but you guys are all working it out really good.
Outdoor air temperature stays below 65 degrees, the crankcase heater will stay energized. When heating is required, the thermostat is set to the desired temperature.
Okay, we are going to start this, and we're going to go over the
We have a problem.
Houston, they have a problem. Yeah, they have a problem.
That's because whenever the limit switch
One.
closes, you get a fan. Okay, you literally circuit of a fan. Or let's say you lose the, let's say you lose that.
Oh, fan is blowing.
Yeah. You lose the second.
They've got the fancy one.
You know, you're familiar with, you know, right? This two right here is this two?
I think one on the top. The top one on the top.
Yeah.
Yeah, the one's on the top.
Yeah. Okay.
Hey, my buddy. Hey. We need you. We need your expertise.
Can you bring it?
I'm professionally grown as big as I'm ever going to get.
I need professional cross so I can get into my next step.
I know. See, I started as a teacher 16 years ago, and they didn't have professional growth. Then, about 8-9 years ago, the legislature decided, oh, teachers should have to go back to school all the time. So, they won't teachers. All they do is drink and drive.
DWP tour. I could use this as professional.
You can use almost anything. Well, you guys did it.
Thank you, sir.
For salary, are you the one way out?